Now we'll consider titrations. Titrations are an important area of chemistry to determine the concentration of unknown species in solution. Say we have a solution and we have a particular acid in solution, but we don't know the concentration of the acid. What we can do is we can take a base of known concentration and we can start adding it to the acid solution, and we'll do it drop by drop. So we have a piece of equipment that will dispense our base solution one drop at a time, and we can measure the exact volume of base that we put into the solution, and knowing the volume and its concentration, we know exactly how many moles of base we've added to the acid. So the acid will react with the base. So looking at the chemical reactions, say we have a strong acid in our solution, and strong acid will produce H3O plus in solution. Say we react that with strong base, then we will just have the autoionization of water reaction, and this Kw here, or this equilibrium constant, is 1 over Kw, which is 10 to the 14th. So this equilibrium constant is huge. So basically, this reaction can be considered going all the way to water. So if we know exactly how much base we put in from a 1-to-1 ratio, we can find how much acid was in the original solution. Now say we have a weak acid, and we'll add strong base to the solution. This reaction will give us A minus plus water. And if we look at this equilibrium constant, this is just the inverse of the conjugate base for a particular weak acid, and those conjugate base equilibrium constants are usually small for weak acids. So this equilibrium constant is going to be fairly large, say on the order of 10 to the 10th. And so this reaction can be considered going all the way. So if we know how much base we put in from the 1-to-1 ratio, we can find out how much weak acid was in our particular solution. Say we have a weak base in our solution, and we react that with a strong acid, and we know the strong acid concentration, then this reaction will produce BH plus and water. So this is just the reaction of the conjugate acid with water. So this is 1 over Ka for the conjugate acid. Those are usually small for the conjugate acid. So this equilibrium constant will be on the order again of, say, 10 to the 10th. So this equilibrium constant is very large. So it basically goes to completion. And so if we know the amount of acid we put in, we can find how much base was in the original solution because we have a 1-to-1 ratio. So how do we determine when we've reacted all of the base acid or strong acid? So we want to know the exact point at which this reaction goes to completion. So we can measure the pH of the solution as we perform the titration. So if we have a curve here, and say we're going to start with a strong acid, and we're going to pipette or titrate with a strong base. So we would have a curve because we have a strong acid. The pH, this is pH here, and this is the volume of base added to the solution. So we have an acid solution. We're going to add a base to it. So we start out acidic because it's an acid solution. We start adding base. So we're going to start reacting the acid with the base that we add. So start adding base and some of the reaction disappears, but it's still an acidic solution because we still have strong acid left over. So we're at pH below 7. So I'll put this at 7.0 pH. So we start at a low pH, and then we'll get to a point where we've just reacted all of the acid. At that point, we just have pure water. So the pH will be 7. So we'll get to a point where we just reacted all of the acid, and now the pH will jump to 7 because we've just gotten to the point of reacting the acid. So now we just have pure water. And if we continue to add base, the pH will climb, and then we'll just keep adding more and more base, and the curve will flatten out a little bit as we add. We have a very basic solution, and we'll keep adding a little bit more base. So we can tell for a strong acid, strong base solution when the reaction is complete by noticing at pH 7 exactly the volume of base added. And since we know its concentration, we know exactly how many moles of base that we added, and we can determine from the 1-to-1 ratio, that's how many moles of acid we started with. So now let's consider titrating a weak acid with a strong base. So here I'll have pH 7.0, and this will be the volume of base added, and we have a weak acid, so we're going to start in the acidic pH region, and when we add a little bit of OH, the pH is going to go up. But then as we add more and more OH, we form A minus. So now we have the conjugate base and its acid together at the same time. So what we've done is we formed a buffer solution. So as we keep adding more acid, we have a buffer, as we keep adding more base, since we have a buffer solution, the pH is not changing very much. And then when we get close to reacting all the acid, we have a solution heavy in A minus, a conjugate base. So the solution is going to be basic close to when we have reacted all the HA, so the pH will be above 7. So we're above pH 7, and then we react all the acid. And then if we add a little bit more base, the pH rises steeply, and then we keep adding base, and the pH will flatten out a little bit. So now our point at which we've reacted all of the acid is above pH 7 because we have a conjugate basic solution. So how do we know when we get to this point where we have reacted all of the strong or weak acid? Well, we can use a pH meter, an electronic pH meter, to tell us when the pH rises drastically, when we hit the inflection point here, or we can use an indicator that will change colors in this pH range. So used to be before we had electronic pH meters, we'd use chemical indicators like phenolphthalein, which would turn pink.